Welcome back to Physics 30. So this will be part 2 of the freely falling section. So we looked at what the position would be after having an initial velocity of negative 3 meters per second. Let's look at what the final velocity would be after each of those scenarios. So actually this should be A, that's not B yet. Here's B coming up. So looking at how far it would be, or what the velocity would be. Now I know the time periods, I know the acceleration, I know the VI, so that would involve using this formula, the acceleration formula, rearranged for VF. Because I know acceleration, I know time that I'm looking at, VI, so this would be what I would use to figure out the VF for each one of those scenarios. So being chucked down at 3 meters per second, negative 9.8. So after 1 second, my final velocity would be negative 12.8 meters per second. And if I had looked at going from 0 to 2 seconds, use the same formula, plus A delta T. So again, being chucked down at 3 meters per second, negative 9.8. After that second, my final velocity would be negative 22.6 meters per second. There we go. So that gives us an idea of what happens when you chuck something down and where it would be. So if we look at that, now the last question here, compare with the velocities of the drop ball, calculating the drop ball velocities after 1 and 2. So if I had just dropped them, so again, I'm going back to the scenario, if I had just dropped them, so VF equals VI plus A delta T. So this part here, of course, is going to be 0 plus negative 9.8 times 1. Whoops. I would have just got simply negative 9.80. So yes, chucking it down with an initial velocity does change it a little bit. And then the other one, let's see, after that extended time of 2 seconds. So 0 plus negative 9.80 times 2 seconds. So we can see here it works out to be negative 19.6 meters per second. Okay, so we looked at using those equations, kind of turned up in a vertical sense using little g as little a. All right, moving on to the other examples. So a ball thrown upwards this time, not being dropped, but thrown. It has an initial velocity of 15. How high does it go? Ignore air resistance. So we can assume we're chucking it up in the air. So VI, I'm releasing it at plus 15. If we assume the upward movement is positive. Now at the very top of the path, that ball is going to stop, then turn around and land again. So at the very top of the path, for that very short time period, VF is equal to 0. It's going to stop at that topmost point. We're looking for how high it goes. We're given nothing about time, so that gives us an indication that we should use this relationship. So VF is going to be 0. Initially we released it at plus 15. Negative 9.8 is my acceleration, and I'm looking for the delta D. So 15 squared, if we figure out what that is, that's what, 225? And then 9.8 multiplied by 2, that's negative 19.6 times D. Okay, so rearranging this equation, be careful. Subtract 225, subtract 225. So we'll get negative 225 is equal to negative 19.6. Hey, this makes sense. I'm going to get a positive result, which makes sense because my displacement is in the positive area. So then divide by negative 19.6. Divide by negative 19.6, and my D is going to be plus 11.5 meter sticks. 11 point, that seems reasonable, 11 meters in the air, if I'm chucking it really hard. Second scenario, as in the previous example, but how long is the ball in the air before it comes back to my hand? Now, here's the interesting part. Throw it up in the air, it stops, turnarounds, and comes back down. It's symmetrical. It's symmetrical in this case. So the T up and the T down are going to be equal. So kind of a trick I can use for this question is that just figure the time up and then multiply that by 2. And I can figure that out. So to figure out the time up, I could use that same acceleration equation that I used earlier. So at the very top of the path, it's 0. Chucking it up in the air at 15. Negative 9.8 is my acceleration. So subtract 15 from each side. And I get negative 15 is equal to negative 9.8 times delta t. And then divide by negative 9.8. And my t is equal to, what do I get there? I think 1.53 seconds. Now therefore, since the path is symmetrical, T up equals T down. Therefore, total time in air is simply 2 times 1.53 seconds, and that's going to give me 3.06 seconds. There we go. 1001, 1002, 1003. That seems reasonable. Now, again, as in the previous example, let's consider again the ball thrown upwards. How much time it takes for the ball to reach the maximum height? Okay, well, we already did that. So it's 1.53 seconds. And the velocity of the ball when it returns to the thrower's hand. Now, this is interesting too. So if we take a look at this path, we could take a look at just the last part of that path. Oops. Make that funky bracket. If I'm just analyzing the last part, I'm going to be looking for VF, so what velocity it hits the ground with. And if I just look at the last part of the trip, oh, from up here, I could consider that to be VI, and VF, it'd be the same as dropping it from that top part of the path. I already know the height of that. Or I don't even have to use it. I could just simply use VF is equal to VI plus A delta T. And of course, VI will be my 0. So it's like my initial velocity. I just dropped it from that top height. I know how long it's going to fall for. It's going to fall for 1.53 seconds. So negative 9.8 multiplied by 1.53 seconds. And of course, a negative times that, I'm going to get 15. So yes, it's symmetrical. So notice if I throw it up in the air at plus 15, it's going to go to the top of the path, be 0 for that split moment in time, then come back down and hit again at 50 meters per second, but in the opposite direction. All right, taking a quick look at the assignment sheet, I think it should be relatively decent. So a stone is dropped from a high cliff. It's seen to hit the ground this time later. How high is the cliff? So note, when you use your formula, you're likely going to get a negative answer for D, but that's okay because it is falling through a negative displacement. But when you're reporting to someone on the street, how high is the cliff? You would just state it as a positive number, of course. Similarly here, King Kong falling down from the Empire State Building. Looks something, okay, it looks more like a rocket here. Here's King Kong, he's going to fall down. Now the building is 380 meters high, so if the building is 380 meters high, when falling down, be sure to report that as D as negative 380. Because if you're falling this way, 380 to get up, but negative 380 as you're falling downwards. So just be careful with that. And we should be able to figure out this relatively easy as well. A ball player catches a ball 3.8 seconds after throwing it vertically. So if the total time is 3.4 seconds, what speed was the ball thrown up with? Likely the best way to handle this question is to split it up in two, just like we did earlier. Split it up to VI, and of course VF at the top of the path is 0. And I think you know what to do with this time to figure out how much is the time upwards. And then continuing on the next page, what's the maximum height? You should be able to do that. Hitting a ball up in the air, you should be able to figure out this one too. It's decent. The kangaroo question, number 5. A kangaroo jumps straight up to a vertical height of 1.45 meters. How long is it in the air before returning back to the earth? So I kind of interpreted this question as being, what is this part? So we're figuring out what is the last part. He jumps up in the air, then from that 1.5 meters. So delta D falling down will be negative 1.45 if we're assuming the kangaroo is here and falling downwards. If it went up plus 1.45, it's going to be falling down at negative 1.45. And so we're looking for that time period in which we're falling down. All right, the best rebounders in basketball have a vertical leap, that is vertical movement from a fixed point of about 1.2. So delta D is plus 1.2 meter sticks. What is their initial launch speed? So again, very similar to those similar questions. VF at the top of the path is going to be 0. And then you can figure out the time up. And then, of course, you know what to do to make that the total time. All right, so you should be okay with that, and we'll see you again.